self-promotion. You know, it's effective but lacks subtlety. I was complaining to Richard about this, and he offered to switch me into the slot on Wednesday between Atiyah and Gromov. So here we are. Okay, so since it's slightly depressing if the first talk of the conference you already don't understand anything on the first slide, I will try to start rather slowly. Okay, so if you're a specialist, I think, you know, open your laptop, check your email and so on, and I will ring the bell when we get to the exercise. Okay, there you go. So, so what I'm going to talk about is my thesis subject, in fact, which I still haven't managed to free myself from, the symplectic topology of Lefschetz pencils. And for concreteness, I want to take my Lefschetz pencil to be anti-canonical Lefschetz pencil. So I start with a variety which has a smooth complex variety. It has an ample anti-canonical bundle, and I assume that I have you know, two linearly independent sections of this anti-canonical bundle. So each section by itself gives rise to a hypersurface, which if it's smooth, it will be a Calabi-Yau hypersurface. That's why this case is nice for me. So the pencil gives rise to a whole family of such hypersurfaces, parameterized by the projective line. Okay? And I will assume, even though because in this case here, it's not really a generic condition, but I will assume that things are generic looking. So, so the generic fiber, let's say the fiber at infinity, which I just call y of this pencil, is smooth. Then almost every fiber is smooth. And the singularities are only the simplest kind, which means nodes. Also, that, you know, two of those fibers, hypersurfaces intersect. The intersection is called the base locus. And I will assume that this is smooth as well, and that they intersect transversally there. Okay? So this is a picture of what we have here. There's the base locus, where all these YZ intersect, and occasionally one of them will have the simplest kind of singularity. So since they all intersect, it's not exactly a fibration, but there's two ways I can get around this. First, I can remove one of them, which I actually called y. And then I can take S over t. Now it's a function on this complement here, which is an affine variety, and it takes values in C. Or I can actually extend this to something that fibers over CP1, and the total space will be what's called the graph of the pencil. You can think of it as follows, that I have the same hypersurfaces as before, just now they no longer intersect, I separated them, or you can think of them as starting from the original x and blowing up the base locus. Anyway, this is the graph of this pencil. This is a fibration over CP1. So those are called Lefschetz fibrations, so they have only the simplest kind of singularities. As another feature here, because I blew up, I have this exceptional locus here, which is a copy of CP1 cross B. So basically, every fiber of this map over CP1 contains the same copy of B. So there's this kind of big piece here, which is sort of sections, which are called the trivial sections. And so more or less, this is a sort of, you know, reversible process. So if you started with something that's over CP1, and it has this kind of big thing of trivial sections with the right normal bundle, you could blow down the trivial sections and get back to a pencil. Okay, so if you want, instead of thinking of a pencil, you can think of a fibration of a CP1 with these kinds of distinguished sections. So the way that you know, everybody likes to analyze the topology of this is by looking at certain cycles. So, so the Lefschetz thimbles. So I start with a critical point. I draw a path in the base, and there will be so draw a path, embedded path in the base, starting at this critical value and not touching any other critical values, and going to infinity in a fixed direction. And over this, there is a unique cycle. It's a properly embedded copy of Rn, like a half-dimensional cycle. It's not a complex cycle. It's a Lagrangian submanifold if you equip the total space with a Kähler form, and this is the Lefschetz thimble. Okay. So this goes out to infinity, but I could stop somewhere here and say I take the fiber at this point, and over this point, the Lefschetz thimble has a sphere, which I call the vanishing cycle. So the Lefschetz thimble is an Rn properly embedded in the total space. The vanishing cycle is a sphere, a Lagrangian sphere inside a fiber, which you think of as a fiber somewhere far out. Or in the case of Lefschetz pencils, we have a smooth fiber at infinity. We could just think of the vanishing cycles as lying in the fiber of infinity. So now I make a choice. Suppose that I have m critical points. I choose a collection of paths like this. And in this notion of how I choose the collection of paths, there's an implicit ordering. So let's say they all go over to the right. They don't intersect each other. And they start at the bottom with 1 and go up to n. And this gives rise to a sort of finite collection of such cycles, the Lefschetz symbols or the vanishing cycles. Okay, this is kind of elementary. They sort of minor nice game to draw these things. Of course, this is not unique. It depends on your choice of paths. How it depends is well known. I'm not going to discuss it here. So when you want to draw it, there's an art in choosing paths which make it look nice. So the simplest example you can possibly start, if you start with CP2, so the anticanonical pencil is a pencil of cubics. It has 9 base points, the intersections of 2 cubics. It has 12 vanishing cycles. And this is one possible way to choose the vanishing cycles. So the ordering is such that it's essentially by the clockwise. So there are 3 parallel ones. It doesn't matter how you order these 3 here. These are 1, 2, 3. The next ones are the ones that go diagonal like this: 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is an example of a picture. And once you have this picture here, it describes the entire symplectic topology of this original map here. Okay, so now I'm going to use flow homology or holomorphic curve techniques to extract algebraic information from this geometric information, from these Lefschetz symbols and these vanishing cycles. And these will be the things that I'm concerned about. And they all come as sort of categories here, right? So which I'll call A and B. And there's a subscript Q, which I'll explain in a little bit. So the first one is the idea is you take the vanishing cycles that lie in the fiber. Those are going to be the objects of the category. So honestly, it's not exciting as a category. It just has finitely many objects. And the morphisms between one and the other, well, if they intersect transversely, there's essentially, the morphisms form a vector space over this field here, field of Laurent series in one variable Q, and there's one generator for each intersection point. Okay. And if I is not equals to j, you can always perturb them slightly to have them intersect transversely, and so this is a reasonable recipe. Obviously, the endomorphism of an object, you can't make an object transverse to itself. So let's just assume the object is a sphere. We choose a Morse function with a minimum and maximum, and we think of 2 generators. Those would be the intersection points if we actually did perturb this thing here. But anyway, so it has these 2 generators of degree 0 and n-1. So I told you what the objects are. I told you what the morphisms are. The morphisms are a vector space. I didn't tell you the actual interesting information, which is the composition laws in this category. Formally speaking, it will come out to be something quite horrible, an infinity category over this field here. Now, I'm not going to give the formal definition, but I want to explain to you the role of this parameter Q because it's important. So the compositions in this category, they count holomorphic maps, and Q essentially is a bookkeeping device for the area, sometimes called the Novikov variable. So the area of holomorphic curves in the fiber. So the area means integrating out the Kähler form. Here I like the Kähler form is Poincaré dual to the base locus. So instead I could just count intersections with the base locus. That makes it a little bit easier to draw. So here's an example, okay? So which is sort of a simplified version. You can consider it as a tiny piece of the computation you would have to do here, but it's just a torus. It has 2 base points here, and there are 3 vanishing cycles, 1, 2, and 3, and they all intersect at one point x. Okay. Now I have the hums from the second to the third is just one-dimensional. First, second is one-dimensional. The first, third is one-dimensional. They're all generated by the single point x. So basically, when I say what is this composition, I have to take x tensor x, and I have to map it to x. And in order to do that, I count triangles here. And each triangle gets counted with the power of q, which is how many of these green dots it goes over. So there is a constant triangle here, which is q to the naught. Then there's this triangle here, there's q, there's another triangle here, q. And then we come with triangles that sort of wrap the torus several times. The next triangle will be this one here, and it actually contains 4 points, and the triangle after that contains 9 points. And again, there's another version over here. So in the end, you get this coefficient here, which is this Jacobi theta function. So this q variable here keeps track of this area. And well, it's a formal variable. As you can see, you probably do not want to set it to 1 here, otherwise it does not converge. Okay. So this is one way to make this algebraic structure. There's a slightly different way, which was originally suggested by Kontsevich, based on classical ideas in singularity theory, which is instead of taking the vanishing cycles, see the previous thing, I used the vanishing cycles in the fiber, everything takes place in the fiber, and the ordering of the vanishing cycles played absolutely no role. Okay? However, the ordering is really important for the topology of the Lefschetz vibration. If you change the ordering of the vanishing cycles, that would represent a completely different vibration. So the idea is to make something which actually looks at the ordering, and in fact, to just look at the intersection instead of looking at the vanishing cycles, look at the intersection of the Lefschetz thimbles. Now the thimbles are non-compact, so the question is should I deal with intersections at infinity? And the way to deal with is to make an unsymmetric perturbation. So this gives another category, A, which has as objects, it has its thimbles, and again I use intersection points to make the morphisms, but now when I make the morphisms from one to the other, I perturb the first one, and the way that I do it is I take the path here, and I push it all the way up, very far, and then I count the intersection points. So here you can see, the original paths, delta I, delta j. This would be a case where I is less than j. The original paths are disjoint, so the original thimbles don't intersect, but when I perturb it, they intersect, and they intersect in exactly one fiber, so the intersection points here, I less than j, are the same as the intersection points of the Lefschetz thimbles. However, if the ordering is the opposite, so I'm going home from delta j to delta I would take this guy here and push it up, and then it would still be disjoint, so then I would get 0. And if you take one, the endomorphism of a single thing, you perturb it, and there's one intersection point, which is here at the singular point. So it looks like this. So basically, you can think of this A as taking, it takes part of the information from B and throws the rest away, using the ordering to decide what to do. So you can think of it as a well, I should say I call these things categories, but they have finitely many objects. So I could just take the direct sum of all the home spaces, just think of it as an algebra. It's less scary. So you can think of this guy here as a subalgebra of that guy. This is the piece that just does the vanishing cycles in the fiber. This is the one we extracted from the Lefschetz thimbles, but actually it lies inside this. And it retains more information in the sense of retaining the ordering, but it retains less information in the sense that you threw away a bunch of morphism spaces that you had before. Okay, now we come to the first not obvious fact, which is first observed by Oru, Katsakov, and Orlov in sample examples, is that this thing here, A, that we just constructed, in many cases, it actually turns out that the dependence on Q is trivial. Now, what does this mean? Now, Q counts these things by area, right? So if I said it's trivial, it would mean, well, all the things have a sort of area 0. That's not what I mean. I mean, it's trivial up to isomorphism. So you can sort of change bases, make some isomorphism, and after that, it becomes trivial, which means there's something defined over C, and it's the base extension of that. So just to get a perspective, so in this case here, this is actually trivially true, because, all you have in the category A are actually these morphisms that increase numbers from 1 to 2, 2 to 3, from 1 to 3. The composition multiplies by this thing here, but you could just change the bases here by multiplying with this one here, and then the composition would be 1. Okay? So because this is, in a sense, in this case, A is sort of free. Okay? But in B, you have things that go back from 3 to 1 and from 3 to 2, so you can't quite play the same game. Okay? So in this case here, it's obvious, but it's also true, for instance, for the cubic pencil on CP2, where things are not free. So you count, you start counting holomorphic triangles, and in fact polygons here, and there are a lot of them. They have more and more and more area. Then you stare at it very hard. You open some kind of book with all sorts of relations between cubic theta functions, and then you figure out that you can sort of cancel out everything. And it becomes independent, which is very convenient because it means that you could just count the small area things, and that would be it. Okay? So for the other version, B, that's not actually true. Oh, by the way, so it's true for the cubic pencil on CP2. When this phenomenon was first discovered, there was a certain tendency to assume that there's some kind of general thing, or maybe general thing for mirror symmetry. But if you take the cubic pencil on the Hirzebruch surface F1, this is actually not true. Okay. So so for B, never happens, at least for Lefschetz pencils. This Q dependence is always non-trivial, which is what you would expect, right? You're counting these things of more and more area. Why should it not contribute anything? However, it's very constrained. And this is one of the main topics of mirror symmetry, to understand exactly what those constraints are. Okay. So excellent. So how do we get a grip on this? So the idea is sort of inspired by mirror symmetry. Now, if you think of mirror symmetry, you would think, okay, I have some kind of object, my Lefschetz pencil, I want to study its symplectic geometry, I should have some other object that is its mirror that helps me. I think, not sure this is the right way of reading sort of Konczewicz's mirror symmetry paper. I think the way that I like to read it is that, these things that we have introduced, these A's and B's, they are themselves geometric objects of sort of non-commutative geometry, and they carry non-trivial geometry by themselves. Okay, so the mirror geometry is the geometry of these guys here, which actually will turn out to be the same as the geometry of the pencil. Okay, so inside the pencil there's another hidden mirror pencil, it's the geometry of that one that actually will determine what's going on. Now, slightly more concretely, okay, since I'm going to sort of dig deeper into this thing here. So if I think of the original Lefschetz pencil idea, I took the Lefschetz pencil, I removed the fiber, you get this fibration over C, and from this you get this A's and B's, and actually a little more, which I will explain. But there's still two other pieces which I haven't used at all so far, which is the fact that the Lefschetz fibration extended to CP1, in fact the fiber at infinity is smooth, and the fact that there are these trivial sections here. Okay? So I have not actually encoded this piece of knowledge into things, and we'll see that I will do that. Okay. Are there any questions up to this point? Yes?
I didn't understand your mirror philosophy at all. Do you want to say it again?
You'll see it.
Okay.
So the next couple of slides, I will explain the necessary sort of non-commutative geometry that I need in order to formulate whatever insights.
Just one question.
Yeah.
Does your non-commutative geometry have any relation with Alan Kohn?
Well, in the sense, it's non-commutative geometry in the sense of the algebra geometric Alan Kohn, right? So there would be like cyclic homology and so on, but they wouldn't be convergent. It would be strictly algebraic geometry. So there's no non-commutative differential geometry. Very unfortunately, I have to say.
Oh, well, that's a gap you can bridge. Yes, okay.
Yeah. Okay, so I want to take certain notions of algebraic geometry and give you the sort of corresponding non-commutative version, starting very slowly, starting with the notion of line bundle. Okay? So usually what's a line bundle? You have a variety, you have a line bundle. The way that I want to think of a line bundle is as something that acts on other bundles. You can take a bundle and you can tensor it with this line bundle, and it's an invertible operation. So if I think of a non-commutative, so in this case, in this world here, a non-commutative space is just any associative unital algebra or DG algebra or A infinity algebra. And vector bundles are essentially modules. Okay, so something that can act. So that's the first decision we have to make, that a line bundle is not actually a module because it's non-commutative and modules don't act on modules. So a line bundle has to be a bimodule, so something that you can tensor with. Right, so it should be a sort of an operation on modules. This is some module category. You tensor with this thing here, and it has to be an invertible operation. So the decision that we make is that, algebraic geometry, they say invertible module instead of a line bundle, but in non-commutative geometry, it's an invertible bimodule. So it's a bimodule, something that's a left module and a right module, such that this operation here is an invertible operation. So let's say there's another bimodule, and if I tensor them together, I get the trivial bimodule, up to quasi-isomorphism or something. So this is our first definition of what a line bundle is. Now we have to think about what's the linear system that's underlying a line bundle. So a linear system is given by sections. So a section usually is a morphism from O to P and to the line bundle, and this is essentially the same thing here is true in the sense of bimodule. So you think of O, this is the trivial line bundle, the diagonal bimodule. And you can think of things as natural transformation for such functions simply as maps of bimodules. So maps of bimodule from the trivial bimodule to P, those are a space of sections. I'm thinking of it to DG world. So there's Homs of bimodules are a chain complex, and I take its cohomology, just like some resolution in algebraic geometry. And I also would like to have sections of the dual or sort of inverse line bundle. They would be like this, Homs from the trivial one to the inverse one, or you can think of this as Homs from your line bundle to the trivial line bundle. And the second one, slightly easier to work with because you don't have to give an explicit formula for what this inverse here is. Okay. So then once we've decided we know what a line bundle is, we would like to know what standard examples are from algebraic geometry, the canonical, the anti-canonical. You know, if you're an algebraic geometer, you know, defining what the canonical line bundle or dualizing sheaf is depends a little bit, can be more or less difficult. So in this case here, there's actually a distinction between anti-canonical and canonical. The canonical one is very easy to define if the DGA is finite dimensional, or at least has finite dimensional cohomology. It's just a vector space dual with a dual bimodule structure. So that's the canonical bundle, and that will play a big role. If you wanted the anti-canonical bundle, well, you could define it as the inverse of this guy here, but for a direct, there's a direct definition. See, I said this is easy, you just take the dual, but that wouldn't apply to many cases, like you know, an affine variety, the ring of functions is not finite dimensional. But we still believe that it has a canonical bundle. But in this case here, it's easier to define the anti-canonical line bundle. It has a sort of horrible formula. And that one works well. So, but I'm mainly going to use, I'm only going to use this simpler one here. Okay, so I think we know what a line bundle is, okay, and what a section of the line bundle is. Now I would like to know what a divisor is, okay? So usually I think that's not really a problem. You know, a divisor is essentially the same thing as a non-trivial section of a line bundle, okay? So in other words, you know, take the section and I take, let's say, take the subscheme where it's 0, or I, you know, take the ring of functions on my ambient variety and divide by this. Well, this is in case I do locally, right? Locally, my line bundle is trivial. I divide by the ideal of sections, and I get the ring of functions on the divisor. Now, in non-commutative geometry, this quotient thing here is a very iffy thing to do. So instead, I would like to do something which is the same up to cohomology, which is to use a resolution. So instead of saying, I look at, you know, the subscheme Y here, I would like to look at the ambient space X, but I would like to put a new ring of functions here, which is actually a DG, a sheaf of DGAs, where I extend the original structure sheaf by the inverse of my line bundle, and I use the section as a differential. So what happens is the cohomology of this guy here is 0 outside Y, and essentially gives you back OY. So this is, I don't know what, a quasi-isomorphism of DG schemes. It's not exactly the same thing as the divisor in the classical sense, because, for instance, in this resolution sense, you can take the section to be 0, and then the divisor would actually be the extension of OX by L inverse. Okay? So, so what happens in this, you know, this resolution thing is I took OX, I extended it by L inverse, which gives you this sheaf of exterior algebras, and then I introduce a differential, which is this section. Okay? So in saying it's an exterior algebra, I kind of use the commutativity of the situation. So in the non-commutative case, that's actually no longer true. So the first piece of surprise is that to make a divisor, you need slightly more than a section. Okay? So, but I copy this guy here, this kind of extension idea, and I say if I have my DGA, I have my bimodule, I take this and I take my algebra, I extend it by this bimodule here. Okay, this 1 means shift down by 1 in degree, so it corresponds to putting it here. And then I put on this whole thing here, I put an algebra structure, which is such that, you know, the original thing is a subalgebra, just like I had the OX sitting in here. And if I quotient out, I get my bimodule P back, but otherwise there can be a bunch of additional information. And if you think about it, the first piece of information that's inside such a construction, such an extension, so there is the trivial extension where you do nothing, which corresponds to S equals 0. But there's a lot of freedom in doing other things. The first piece of information is indeed a map of bimodules from P to A, which is like the kind of differential, which would appear here. So this is a definition of a non-commutative divisor where the underlying line bundle is the inverse of P. In generally speaking, this I call the leading order term, it's just a section, but generally speaking, there is more information in this non-commutative divisor than just the section. And there's some kind of obstruction theory where you can,
well,
yes?
So if you had just taken the definition of the section to be just an element of the Hom rather than the H
Yes.
of the Hom, then the story, wouldn't it look cleaner?
Well, the point is, you know, the divisor is supposed to be a space, meaning an algebra, right? And there's just no way in non-commutative geometry that you can make it starting from just a section.
Well,
Okay? So I want the divisor to be a space. Was that?
I mean,
So for, you know, of course I could just declare a divisor to be a section, but, or an equivalence class of sections, but I want the divisor to be a space by itself.
Sure.
Okay? And for that you need extra information.
but extra information is an element of the Hom, not H naught.
Oh, I could define it. Well, but there's a notion of isomorphism of non-commutative divisors, and under isomorphism, only this guy here is preserved. Yeah, so, you know, the things on the chain level things are always very iffy. So let's call this here the. So this is the first piece of information. And, well, if you go back to the case of ordinary algebraic geometry, this is the only piece that matters because all the other pieces lie in X groups of negative degree. Okay, but that's sort of an accident. So this is non-commutative divisor, and now I would like to do non-commutative pencils of divisors, right? So a pencil of divisor is a family of divisors that parameterize by the projective line in some kind of linear way, or rather you could say it's it's some kind of homogeneous family that's parameterized by the affine two-dimensional affine space. Well, you think, well, this is not exactly the same because, you know, when you think of a pencil of divisors, right, it's parameterized by P1. Well, you can say, okay, it's parameterized by A2 minus the origin, but what sits at the origin, right? But in this case here, you know, this extended notion of divisor has sort of the trivial choice, and we can stick that in as the origin, okay? So, to give you the maybe more detail that you want to, so we take our two-dimensional vector space, which is the one that's right here, but I call it a V just for. I take my original thing, the algebra, the bimodule, and I want to, for organizing purposes, I want to introduce a grading which I call by weight. It's nothing to do with really weights, but I think of it as being an action of the multiplicative group. This is weight 0, this is weight -1, this is weight -1. So if you look at the non-commutative divisor structure on this thing here, the pieces actually all have non-negative weights, and the pieces that have weight 0 reproduce the basic structure of the algebra A and the bimodule P. So the same thing, now I take a non-commutative pencil. So again, it's a structure that lives on B, but it's not a single algebra structure. It's sort of a structure that is parametrized by the symmetric product of V. So there's, you know, you can specialize it by choosing an element of the dual vector space to V, and then it becomes a non-commutative divisor, and there is some homogeneity with respect to weight, and that organizes everything. And so this is the notion of a non-commutative pencil. Takes a bit of time to get used to, so maybe you don't have the time here. Again, you can extract a leading order term which consists of a pair of sections. They don't have to be non-zero, they don't have to be linearly independent. It could be any sections. And the other stuff, you know, you have to think about it. It works. Some stuff works as you might think. So, you know, obviously if you have a pencil, it gives rise to a family of divisors up to isomorphisms, parameterized by the projective line in this dual here. And you have other elements, such as, for instance, the base of the pencil. So the base of the pencil actually works like this. So you take these two non-commutative divisors, look at them as bimodules over A, and tensor them together. That's just like the Kosul resolution. That gives you the intersection, here we start, you know, when you start digging a little bit deeper, things start getting slightly uncomfortable. So this base locus here is a bimodule, but it's not an algebra, so it's not an actual space. So, of course, the base locus should be a space. There I'm sort of already at the end of my understanding. There's a different definition of base locus, which is a space, but which may or not be the same as this thing here. There's all sorts of things. So you can ask yourself, you know, this blow-up thing, there's the graph of the pencil, that exists, there's a definition of graph, and so on. And you can actually you can ask yourselves what are the singular fibers of the pencil, what type of singularities do they have, and so on. So this is what I mean by the non-commutative mirror geometry. And it didn't involve constructing a different space. Well, sorry, I haven't actually applied it yet. Okay, so let's go back to Lefschetz pencils. So I want to apply this to the Lefschetz pencil idea, and of course this is sort of going backwards. You know, we looked at these two kinds of algebraic structures. One, that B that I did in the fiber, and A that I did with the Lefschetz thimbles, and A set inside B. And if you look what I threw away, so, you know, I said when you define A, the ordering is important. So, you know, the Homs from the first to the second cycle you keep, but the Homs from the second to the first you throw away. But actually these things are dual to each other. So they're the same. After all, the intersection points are the same. So if you think of it as just a vector space before you put on all the structures, in fact, B is the direct sum of a copy of A and a copy of the dual vector space. Okay. And now that we have these definitions, you know, the reformulation is that this guy here is a non-commutative divisor associated to this bimodule here, which is essentially the canonical bundle up to a shift. Okay, so the canonical bundle. So, but well, okay, sorry. It's an extension by this guy here, but of course that means that the underlying linear system is the inverse of this. So it's the anti-canonical bundle. So the situation that we have is we have a non-commutative geometry situation where we have a space, which is A, and we have an anti-canonical divisor, which is B. Okay, and that's what I mean by mirror geometry. So now it looks like in non-commutative geometry. So in fact, if you have the anti-canonical Lefschetz pencils, you know, this leading order term, and I put in a parameter Q just to remind ourselves that the ground field of these things has this formal variable Q in it. The leading order term actually determines this guy here. So this situation here, this fact that, you know, in non-commutative geometry it looks like a space with an anti-canonical divisor, that's true for any Lefschetz fibration over C. What I think is that if the Lefschetz fibration extends over CP1, I'm starting to use more geometric features of the original situation. This category here carries the structure of a non-commutative pencil, and this guy here, this divisor, is only one of the fibers of this pencil. Okay, but good questions, what is the geometric meaning of the other fibers? So in general, this is a conjecture. So you have to, you know, non-commutative pencil comes with these structures here. You have to provide these structures here. In the case where Lefschetz fibrations come from an anti-canonical Lefschetz pencils, you know, this is known to be true, but it's not nice proof because I just used some kind of obstruction theory to show that you only need to construct these two leading order terms here, which is a little bit, makes, you know, your life easier. Okay. So this first expectation is that if you start with in symplectic geometry extends over CP1, what happens in this, you know, hidden mirror geometry is that you get the structure of a non-commutative anti-canonical pencil. And moreover, the conjecture is, which I'm not going to talk more about, if your Lefschetz fibration extends over CP1 and the fiber at infinity is smooth, which was the case for Lefschetz pencils, then the corresponding non-commutative pencil has empty base locus. So define the base locus. The idea is it's empty. So in fact, the mirror geometry is actually a fibration over CP1. The base locus is empty. Okay, so the question is, you know, where does this structure that I'm expecting here, where does it actually come from? Okay, all right. So I'm looking for a non-commutative pencil on this guy here. So the leading order term is given by two elements of this hideous group here. So how am I going to construct two elements of this hideous group? Well, there's a geometric way to do it, which is there's something called open-closed, or I guess closed-open string maps. They start from something which is more geometric, and they go into here. And in this case here, start from an object that, you know, I think was already talked about here in 1994, the fixed-point Floer cohomology. So I have an automorphism, in this case here, a symplectic automorphisms of the total space E, and it's fixed-point Floer cohomology, which somehow counts fixed points, and from that there's a natural map into here. So what I want is I want to identify the necessary pair of elements here which will give rise to the non-commutative pencil. So I'm going to give you a slightly naive picture here. So so this automorphism, I call it mu squared because it's a square of another thing mu, but you can just ignore it. This automorphism is an automorphism of the total space that's essentially fibered over the base C. Okay. So let me show you how it's fibered. I'm sorry, maybe this you know, outstripped my artistic abilities. Okay. So this is the base C. Okay. So there is of your Lefschetz pencil. There's a large compact piece here which contains all the excuse me, critical values and all the interesting topology in a sense. And over there it's the identity, this automorphism. Then it starts to rotate slightly clockwise, and it rotates more and more until it rotates by 2 pi minus epsilon, so it's a slight anti-clockwise rotation. And here it ends at a cycle which has this hyperbolic fixed point here. Okay. And then there's another region where it's sort of, you can see, okay, so this is the slight anti-clockwise rotation here. Okay, so near it, it's still anti-clockwise rotate. The other dynamics is you come out of here and you go around here. So in the middle, there's this region here where there's a small rotation on the boundary, and in the interior of the region, there's another fixed point here, an elliptic fixed point. And then, well, after you've done past this thing here, the effect on the outside here is, again, a small rotation. You're going to increase the amount of rotation until you're 2 pi minus epsilon, and then there is another hyperbolic fixed point. And this is the dynamic. And then at infinity, it actually looks like a translation going up everywhere. Okay? So what I have here is I have this big fat component here, which is the identity. And this is the origin of the first leading order term sigma, the one that gives you the original non-commutative divisor. And that exists for any Lefschetz fibration over C. Okay? Here's always the same. The fixed point here is just the identity. Now, what happens over here is, this is a fixed point in the base, but if you look at the flow that we've defined, the flow is actually a rotation by 2 pi. So in the fiber over here, something is happening, which is the monodromy of the original Lefschetz pencil. Okay? But if your Lefschetz pencil extends over infinity and the fiber at infinity is smooth, that monodromy is just the identity. More generally speaking, if it extends over infinity but the fiber at infinity is not necessarily smooth, the flow homology in contribution inside that fiber will have a distinguished generator coming from sections going through infinity. So you use this pink guy here in the middle to give you the first element of the non-commutative pencil, and that guy here to give you the second element. This is a slightly simplified picture because obviously this flow homology, you can't just say, I pick my fixed point. You have to show that this represents a well-defined class, and so on. Okay, but this, I thought it would be nice to have at least one picture where there's some actual geometry happening. So, okay. So, even though it's a lot of it is sort of conjectural or speculative, let's take into account what is the original features of the geometric situation and how have I used them. So I started with, I could say if I have any Lefschetz fibration, I get these categories, A and B, and we know that B is a non-commutative divisor. Now I said if it extends over CP1, you get, in fact, a non-commutative pencil, and the original divisor is just the fiber at infinity of the pencil. If the fiber at infinity is smooth, conjecturally, the non-commutative, there's some expression for what this means in terms of this non-commutative geometry. So when I thought about my original Lefschetz pencil idea, the only thing that's left that I haven't used is this kind of existence of trivial sections here. Okay? And this actually turns out to be, in looking at this, every checkbox represents sort of 5 years of my life, realizing it. And about 2-3 years ago, I got here. So I need to talk a little bit more about algebra. And here it'd be important that our ground field is this field that has this, it has this formal variable q. So you can, formally speaking, you can differentiate with respect to q, right? And I really, when I say you have an algebra over this thing here, I really want to think of you as a sort of this formal family of algebras over an infinitesimal punctured disk. Okay? And I'm asking myself, how does this depend on Q? Okay, and we can differentiate in Q direction. So if you were in algebraic geometry, you have a family, there would be a Kodaira-Spencer class. If you have say you have a vector field on the base, you can say, well, I try to differentiate with respect to the vector field, and I get a class, the Kodaira-Spencer class, that tells me how does my family actually change. Okay, so that's true here as well. So what happens is there's a class, it's called the Kaledian class, which describes what the dependence on Q is. Okay, so well, it's not actually hard to define. It's just you take d by dq. Okay, so this thing here is a vector space over this field. So you can extend this d by dq to a derivation. Let's say you choose some basis of this vector space and you differentiate with respect to that basis. Okay, and then obviously the algebra structures, everything that's interesting, will not be constant. It will have some derivative, and that derivative gives rise to a class and something called the Hochschild cohomology class. You can think of it as Homs from the diagonal bimodule to itself. So this class here that measures differentiation, the sort of infinitesimal dependence of the algebra structure on Q, and it's called the Calabi class. Okay? So this is an infinitesimal class. Now, if you thought about it, algebraic geometry, you have a family over a punctured disk, and the Kodaira-Spencer class is trivial, so infinitesimally the family is trivial. That doesn't actually mean that the family is trivial, right? Because there can still be monodromy. It just means it's infinitesimal trivial. That's also true here. However, if you instead, let's say, if you instead worked on, I'm going to sort of disregard this a little bit. If you instead worked over just formal power series, which means over the disk, which is simply connected, then if the Calabi class is trivial, then that means that the Q dependence is trivial, in the sense that I said it before. Okay, so which means there's some up to isomorphism, there's some structure defined over C, and this original thing is just the base extension of this. Okay, so, and we saw before that this is a phenomenon that does occur. So, okay, so let's think about Fukaya calculus. So the first thing is these things that are done in the fiber. Okay, here there's a similar, I'm going to use the same trick as before, some kind of open-closed string map, in this case here from the cohomology of the fiber to the Hochschild cohomology of this thing here. And the Calabi class has a geometric meaning. It's the image of this guy here, Q inverse times the cohomology class of the Kähler form, or the cohomology class of the some divisor representing the Kähler form. This is not actually hard to see. It's what they call the divisor axiom in Gromov-Witten theory. Okay. Now, in many cases, and in particular in all cases coming from anti-canonical Lefschetz pencil, this map here is an isomorphism, and this class here is always non-zero, so therefore this class is always non-zero. So, well, okay, but you know, for this guy here, we didn't expect the Q dependence to be trivial, right? It's the other guy, A, for which I expect the Q dependence to be trivial. Okay, so let's look at A. Okay, so again, there's an open-closed string map, and the thing that's responsible is the fixed point flow cohomology of something like this. It's actually simpler. It's only the thing it's actually the flow cohomology of mu. So that means you have these fixed points, and you have the hyperbolic fixed point here, and all the rest disappears. So you have a copy of the cohomology of the total space, and then you have the stuff that comes from here. But there can be cancellation between those two things. And so what happens is you have a map, as before, from the ordinary cohomology. Sorry, I forgot to put in the coefficient field. From the ordinary cohomology of the total space to what you want, and Q inverse times the cohomology class of the Kähler form still goes to the Calabi class. Okay? So before that, this was an isomorphism for B, and that was the end of it. But here you have the things that come from the hyperbolic fixed point, which is a copy of the flow cohomology of the monodromy, or in this case here for pencil, it's just the cohomology of the fiber. And there's a map here. So if this guy here gets killed by this map here, then it will go to 0 here. Okay? And this map here has a geometric meaning. In our case, so say we have the Lefschetz fibration that extends over infinity, and this thing here counts holomorphic sections. So the way that you want to think about this thing is you have a cycle in the fiber over infinity, and you look at all the holomorphic sections that pass through that cycle, and you see what they span in the rest of the manifold. That gives you a cycle of dimension 2 higher. And this is here what it goes. Whoopsie, whoa. Okay. This is this map here. In particular, you know, if you start with the class 1 here in H0, it will go to some class in H upper 2, which is Poincaré dual to the space that's spanned out by all the sections. Okay? So let me introduce some notation here. Okay? So when I count, so I have some, you know, now I'm looking at this graph, at this blow-up, which is fibered over CP1. I look at all possible homology classes which intersect the fiber multiplicity 1, so the classes of sections. For each of them, I can see what sections there are. That gives you a class in H2. This is kind of a Gromov-Witten invariant. And I sum over all those classes, well, with the area, in this case here, you know, the intersection with the base locus. Okay. So this is the image of the element 1 under here, is this count of sections here. Okay. So now, I'm really thinking of the case of Lefschetz pencils. So there are these trivial sections. Okay. The way that I've organized it is so these trivial sections span a copy of this blown up base locus, CP1 cross the base locus, and they're the only ones that actually come with because of the normal bundle, they come with a negative exponent, Q inverse. The rest all come with non-negative exponents. Okay. And moreover, you know, I wasn't quite clear about the cohomology classes of Kähler forms that I'm using here, but there's two natural cycles, which is this blown-up base locus and the fiber. And the natural cohomology class of the symplectic form is this thing here plus some large multiple of the fiber here. So if you restrict it to the complement of the fiber to the part over C, you just get the Poincaré dual of this guy here. So in other words, this guy here is essentially the cohomology class of this space of trivial sections. And you'll see that the trivial sections are actually trying to kill it, right? So they're trying to make this guy here 0 by mapping to it, except there could be other sections which sort of interfere with this, okay? So this is where I'm actually using the existence of trivial sections, okay? So the consequence of this thing here is that if there's no interference, so if you count all the sections, and you get something that lies in the subspace spanned by the two obvious classes, the fiber and the blown-up base locus, then this category will depend trivially on the parameter. Okay? And that's why it holds in some cases, but not in others. It's a feature of enumerative geometry. Okay, so now, I want to focus on the case where this thing here actually holds. Okay? So what we had is, let's say we have this A, which is a non-commutative space. It has this dependence on Q, but we now know that the dependence on Q is actually trivial. And we have, let's say, the non-commutative divisor, B. Okay? Now, if A depends trivially on Q, then B is a family of divisors on A varying with Q. And we can ask ourselves, how does it vary? Okay? All right. So this is there's a lot of information on this slide here. So let's start here on the right. So this is what I just said. So the idea is, A depends trivially. So then the question is, we have a non-commutative divisor. How does it actually depend on Q? And the answer, roughly speaking, is that in this mirror geometry, we have the non-commutative pencil, and the divisor just moves inside the fibers of this pencil. Right? So the space of all these fibers is like a CP1, or two-dimensional projectivization of a two-dimensional space, and it moves in some way. And so we should be able to describe how it moves. Okay? And this will describe our original non-commutative divisor. So, okay, so the way that this turns out is now we need to, I need this motion. So there will be something that, some motion on CP1, which is described by a second-order ODE. So this is the second-order ODE. It's just an ODE for a function, and it's got all sorts of, for a function alpha. And it's got all sorts of coefficients. So first of all, the assumption in the previous theorem was that if I count all these sections, it lies in the subspace that's generated by two cycles. In fact, I can also write it like this, that this thing here, which is the class of the blown-up base locus, is spanned by these two classes. And I want to extract the two coefficients and call them psi and eta. Okay, this is always non-zero because of the existence of trivial sections. So this gives me two functions, psi and eta. They're essentially extracted from this Gromov-Witten invariant Z1. I can also look at bisections, so things that have degree 2 over CP1. The bisections, their index there is so that if I fix a point, there's a discrete amount of sections going through that point. So if I count them, I get a class in H0, which I can also, this thing should not be there. It's not invertible. Which I call Z2 because of degree 2. Okay? So this is another function. So there are three functions of Q, psi, eta, and Z2. And I write down this differential equation here. Okay? Well, why is it exactly this equation here? I would need a very long time to explain. But so this is essentially the variation of the non-commutative divisor in Q. But let's just look at it. So this is an equation for a formal function of Q. So for a formal power series in Q, it's a second-order linear ODE, so it has two linearly independent solutions. Let's say one that starts with Q and one that starts with 1. I take my two linearly independent solutions, and I take their quotient, and that sort of homogenizes the situation. And then the conjecture, which is sort of some way towards being proved, is that this category here, which was the one of the fiber, so in this situation here, for A, the Q dependence is trivial. For B, the answer is the Q dependence is such that everything is, up to isomorphism, everything is polynomial in theta. So there's some algebraic structure which is defined over a one-variable polynomial algebra, and such that if you think of the generator as being this function theta, you get back this q. Okay, so basically this means that after some suitable amount of base change and manipulation, all these infinite series in q that you saw are actually polynomials in theta. And that's actually a more precise statement. You can say exactly what degree the polynomials are. So the q, once you know this theta here, which comes from the enumerative geometry, the q, it completely governs the q dependence. Okay? So in particular, you could actually not set q to be a number, right? Because it's a formal variable. But you can set theta to be a number. That's slightly scary, right? Because it gives you some kind of convergence statement. Now, what happens is, is that this structure here is, well, I don't know, but it's not a priori an invariant. This thing here is essentially a symplectic invariant of the fiber, the Calabi-Yau fiber. This one here is not. It's actually constructed using the pencil, at least a priori. So, so you could imagine the same Calabi-Yau being the hypersurface in two different pencils, and it wouldn't necessarily be the same structure here. In fact, probably not. But now that you have this thing, it depends on this parameter theta. You can ask yourself, well, if I set theta to be 1 or 2 pi I or something, what happens? When is it singular? And so on and so on. So, yeah, so there's some sort of working on this. Been working on this for a while, but it's either I will get done with this or the apocalypse will happen. Over the last year, it seems like the apocalypse made a lot more headway than I did. So I have one more comment to make, since we're here in the sort of, world of 19th century ODE, formal ODE analysis, right? So the way that I set it up is, I said, which is I think the way that geometrically makes the most sense, to say that we take the second order ODE, we take two linear independent solutions, and we take their quotients. But there's also a direct way to describe this quotient here, which is, if you have a second order ODE and you take the quotient of two linearly independent solutions, it solves a nonlinear third order equation, which is a Schwarzian differential equation. So this is the Schwarzian operator here. It's a third order nonlinear operator acting on this function theta by differentiation. And if you have a second order ODE like this, you translate it into an equation for the quotient using the Schwarzian. And the coefficients, there will be an inhomogeneous term here, which is extracted from whatever you had here, from the coefficients here. And in this case here, it looks like this. So if I wanted to give a talk and I wanted to be more mysterious, I would just say, well, the secret of this Q dependence is in this function theta, which solves this strange equation here. It's fun to see what happens in actual examples. So for instance, the cubic pencil on CP2, you write down this equation. And so what you need to do is you need to look at the enumerative geometry of the total space, which is the enumerative geometry of the rational elliptic surface, which is fun. Okay? And in the end, you turn out with this guy here. It's very simple, in terms of the Eisenstein series, E4. Okay? And you can solve this theta here. And, of course, this has been, in this case here, we're asking for the Q dependence on an elliptic curve on a 2 torus. This, of course, extensively studied. And you get this theta is the I think it's best to say the inverse of what's known as the mirror map for a particular family of elliptic curves. And this mirror map was obviously all over the literature, and it was known that it satisfies this Schwarzian differential equation. The reason why it was thought to be is because when you derive it from mirror symmetry, you derive it from a Picard-Fuchs equation. And in this case here, which is a one-dimensional case, the Picard-Fuchs equation is a second-order equation. Okay? However, in fact, this Schwarzian equation is actually a feature in all dimensions and have nothing to do with Picard-Fuchs theory. And if you look at the literature on mirror symmetry, these Schwarzian equations, they sort of, they occasionally emerge for particular things, particular families of K3 surfaces, and then they're sort of swept under the carpet again. But in fact, you need, for this case of mirrors to pencils, they're sort of intrinsic to the mirror geometry. And that is the end.
Any questions?
Yeah. So I have the privilege of the elderly statesman. 2 comments. I'm probably the only person here who knew Lefschetz, but that's a small point. Secondly, I think it's fascinating to look at the origin of the letter Q. Now, you can trace that back to, it's fantastic. Why would P become Q? Because it was the next letter after P. P stood for prime, you had to have another letter, you called it Q. Gauss used Q, and then of course Q happens to be the first letter of a lot of names. Quantum, Quillen, and a lot more. So Q appears everywhere, and it's very fascinating. What is Q? And it is a mysterious object. Q is the universal ghost of the story. And there was a famous English writer called Arthur Quiller Couch, who wrote under the pen name of Q. So I always thought it marvelous to write a book story about who is Q. And the history of all the subject is, if you understand Q, you've understood everything that Paul said and a lot more.
So on one of your earlier slides, in your list of dictionaries,
Yeah.
you had the smoothness of the fiber at infinity being emptiness of the base locus.
Yes.
I didn't understand that since.
Well, emptiness of the base locus of the non-commutative pencil, right? So you have this one here. This is the base locus.
What does empty mean?
Empty means it's this is in particular it's a chain complex and it has zero cohomology. It's a cyclic, quasi-isomorphic to zero. Empty, sorry. Yes.
But somehow, if I take a pencil of terms on a four manifold, there's this kind of interest. I mean, somehow the base locus shows up as one of your enumerative invariants. It counts. I mean, if I think vaguely at space level, if there was a space there, it should be counting your trivial sections. So I'm sort of puzzled that it's also a cyclic.
No, I mean the base locus of this non-commutative pencil is not related to the original base locus. So things look the same, but the pieces move around. And if you ask somebody in mirror symmetry, say Gross-Seibert style mirror symmetry, Julia somewhere, there you go. She would probably tell you that yes, in the Gross-Seibert construction, if you start with the relative to divisor that's smooth, that will cause the mirror to actually be phi-bert over CP1 and not to have base locus. And here this is the meaning of this without saying any words related to mirror. So yeah, so that base locus here doesn't have anything to do with the original base locus. Why that is the case?
You're saying the mirror is an LG model, so it has no base locus.
If the fiber at infinity of the original thing is smooth, but if not, then it has base locus.
It's just saying that the relation between theta and Q is related to mirror map in one-dimensional case, but it's not in high-dimensional case.
Well, no, I mean I assume that it's always the same thing. Well, okay, gosh, this question always makes me very, very nervous. Okay, so my understanding of the mirror map, not very good, is the following one, that on the symplectic side you have this canonical parameter Q, okay, and on the algebraic geometry side, a priori, mirror is parameterized in some way, and you want to see how relate this to this canonical parameter Q, and that's the mirror map. Here it's sort of more the inverse. I'm going to, this non-commutative pencil has a linear parameter on the mirror, and I'm just transforming Q into this linear parameter. So no, I expect that to be the same map, but there's no Hodge theory here. So it's not derived from Hodge. Instead, it's derived by looking at this non-commutative geometry of the mirror more closely and saying this is what I want to do. But I haven't proved that this is always the same.
You were working in a complex situation, but would all the constructions work for a purely symplectic?
Yes, everything would work for purely symplectic ones. I just used the complex one for convenience, so I don't have to.
So the final conjecture, I lost track, is that just for the Fano case?
So this is particularly for the Fano case and for anti-canonical pencils, but you can say something for the more general case. It just takes me more effort.
Because you might imagine that there is some sort of classification theorem of anti-canonical. There are only finitely many Fano manifolds, so
that's correct.
Whether there are only finitely many symplectic Fano pencils would be interesting.
Yes. Right. So usually well, I'm not really very good at this, but yes. So in algebraic geometry, of course, there's only finitely many Fanos of each dimension, and usually you would say, to a Fano or a symplectic Fano, I can associate certain Hodge theoretic data, and that looks like it's a very constrained situation. And the same thing is true here. You get this non-commutative pencil, and it looks like it's a very constrained situation. I can't really use it to do anything in the sense of finiteness theorems, but it's not out of the question. What happens in the situations where you don't have an anticanonical pencil is that the mirror geometry, for instance, you have something on CPN, but it has different degree than n+1. Then the mirror geometry actually is homogeneous. It's a pencil that has a C star action. So then all the information is located at the fibers at 0 at infinity, and it's kind of less nice as a mirror geometric object. So I like this case. This is nice. There are other cases you can do. I obviously have hopes that this will say something about the deeper structure of anticanonical symplectic pencils, but that doesn't really go beyond hope at this moment.
Okay, great. Let's thank Paul again and then meet in half an hour.